So we are in frequency domain. The next video, this is the second video of this chapter. Serial parallel equivalent elements, that we will be seeing another equivalency concept about the source transformation. So these are the equivalent circuits which has got some advantages in frequency domain with respect to time domain. And we will be seeing general analysis techniques, specific analysis techniques. These are seven Norton equivalent circuits and the new element mutual inductance in this chapter. So this here, the second frame. So this video is related to this frame. Let's go in. Go in details about frequency domain advantages on time domain. So we are saying there are some advantages, disadvantages in time domain and frequency domain. So there is an optimization. Some of the things are easy and in frequency domain, but there are some restrictions on the other hand. So in time domain, only serially and parallel connected resistors, capacitors, inductors within themselves can be replaced by an equivalent resistor, capacitor, inductor. This is not true for the mixture of these elements. In time domain, two resistors connected in serial, two capacitors connected in serial, two inductors connected in serial corresponds to one element in sequence: resistor, inductor and capacitor. In frequency domain, serial parallel connected, any mixture of the resistor, capacitor, inductors can be replaced by an equivalent impedance. So that means this is something that we could do in this domain, but we cannot do in time domain. So what is it? Let's go in. Serial connections, parallel connections. So what is the similar one that we have seen in time domain? So serial connected to two or more impedances seen here. We are saying impedances here because the coefficient that we have seen in frequency domain might be complex numbers. When it is complex numbers, we give a special name for these parameters and we call it impedance. So here we've got impedances, they are connected in serial. Just remind you what serial connection is. If two or more elements are connected with their one terminals to a node, and there is no any other element connected to this node, then these two elements are called serial connected. So here you are. So what we are saying is this: if you have the serially connected impedances like that, if you replace all these impedances with one impedance of which value is the summation of these impedances, then this current that we observe in the first circuit and in the second circuit and VABs are going to be the same. VAB, since it is an independent source, voltage source, they are going to be the same in these two equations, in two circuits. But this current here, whatever we measure here, is going to be the same as this. Then we can say this is the equivalent of these impedances connected in serial. So it is easy to prove, so you could do it your own. So what happened here, the number of nodes has been decreased. So in here, how many nodes we have? Apart from this ground node, we've got n nodes here. So in here, apart from the ground node, we've got only one. So n nodes disappeared and one node is seen here. That means the number of node equations that you're going to write is going to be just one in this case. Serial connected elements currents are the same. So current of Z1, Z2, point, Zn, they are all the same. That means the phasors of those elements, currents phasors, are also the same. VAB voltage and I current will be the same in both circuits. We already said that. So when it is parallel connection, so we are saying if you replace, so these are parallel connections. Just remind you what parallel connection is the connection of the corresponding two elements terminals together, means these two elements are connected in parallel or connected in parallel. So here you are, that's n elements are connected in parallel. Just remind you here, written inside not the impedance but admittance. Normally in the circuits we do write the impedances. Why we wrote the admittances here? Because it is easy to explain the equivalent admittance in terms of these admittances. In here, if the elements are connected in parallel, then the corresponding equivalent element admittance is the admittances of these elements. If you write this equation in terms of impedances, you're going to write 1 over Zeq, 1 over Z1, 1 over Z2, 1 over Z3, point, 1 over Zn. To make it easier, we wrote the admittances here. So admittance is the inverse of impedance. So what we see here, we've got meshes, m number of meshes, so this m number of meshes becomes just one mesh. So drastically number of meshes disappears, and this current here, whatever this current here, is going to be the same as this, so that's why it is equivalent element. So we could use that point in order to prove it. When it is parallel, all these elements are parallel connected, all the voltages are the same. In here, when it is serial, currents are the same, in here, voltages are the same. Now let's see on an example what the advantage we have in the frequency domain when we compare it with the time domain. So the third frame comes in. Here we have a circuit here which includes an inductor and capacitor and resistors in it. It is a serial parallel connected circuit. Why it is serial parallel connected? Those two elements are connected in serial. If you replace equivalence of these elements, then it is going to be just one impedance. This impedance are in parallel in this resistor. If you replace it with another impedance, then this impedance becomes serial to this one. So it is serial parallel connected element. Now if you transfer this circuit to the frequency domain, we are going to write the impedances. The impedance of this inductor is 10J, and impedance of the capacitor here is minus J 100Q. So in frequency domain here, let's start from the time domain. In time domain here, you cannot replace those inductor and capacitor with one element. Why is that? Because the definition relations format is different. Both have got the derivatives in it, but in here you're going to take the derivative of the current. In here you're going to take the derivative of the voltage. So the variable of which derivative is going to be taken becomes different for those two elements. That's why we cannot replace it just one element. But in frequency domain, the definition relation of this is VL equal 10J IL, and in here VC is equal minus J 100 IJ. So that means These are serially connected, currents are the same, so you could add the impedances. So if you add those two impedances, that means minus 90, that is the equivalent impedance for those two serially connected inductor and capacitor. We said we cannot do that in time domain, but you could do it in frequency domain. So in this case, this impedance is connected in parallel to this 20 ohm, so you replace it with another impedance. This impedance is serial with this one, so you could put this one. So this serial parallel connection equivalent elements helps us to improve our analysis circuits like this, serial and parallel connected circuits. How it helps us? We said you can replace all these elements and end up with one element and one source here. So that means you can find this current. This current is going to be the same as this current because of these equivalencies. So that means after do that serial parallel connection replacement, we can easily find this current. Independent voltage source, of which impedance is 10 to the power e to the minus e to the power j 30 degree. Over this impedance, you can find that current. That current is equal to this. So you might say that, okay, we have found only the one current phasor in this domain by using the serial parallel connection example, but in analysis, what we understood, find out all the elements, current and voltages phasors. We haven't found that. What we are saying, once you found this phasor of this current, 10 ohm resistor current, you can find all the elements, current and voltages. How? So you can come here, you find this current phasor. If you multiply it with 10, you get the voltage of this resistor. Independent source voltage phasor minus this voltage, you get this voltage, 20 ohm resistor voltage. You find this resistor voltage phasor over 20 gives you this element current. You know this current, you know this current, you can find the current of the inductor. That means phasor of this inductor. Phasor of the current of the inductor. So this current is also the capacitor current. If you know the current of these elements, you can find the voltages of these elements. So what we are saying, this serial parallel connection equivalent impedances helps us to do analysis of serial parallel connected circuits. That is the advantage of the frequency domain when you compare it to time domain. So it is worth examining. So this video is about this frame, so the next video is going to be about the source transformation equivalent circuit and their usage in the circuit analysis. So stop here.